Welcome everybody, my name is Quentin Ledebert. I am the team leader of our product definition engineering group here in America. And today with me I have from AnDAPT, Judith Baker, Marketing Associate, and Rand Goman, Application Engineer. And together we're going to talk about custom power management IC and REDEXPERT software. Please keep your questions for the end. I will have because we'll have a special section for Q&A at the end of this presentation, and you will be able to ask your question live to the speaker. Now, without further ado, I'm letting Judith talk us through AnDAPT history and business model.
Hello, and welcome to AnDAPT, a pioneering and patented new genre of analog digital PMICs. AnDAPT is short for adaptive analog. We are revolutionizing the power management market with a disruptive software-defined power solution. AnDAPT's unprecedented programmability gives customers the means to create and customize a PMIC within minutes. The technology allows for quick customization of a common silicon base consisting of integrated FETs, drivers, uncommitted comparators, ADCs, analog elements such as sensors, and others which are embedded in a programmable fabric. These elements can be configured to form various power delivery topologies, including boost, buck boost, LDOs, load switches, and many more, along with logic gates and sequencers. These form a custom PMIC to build a complete system solution. The technology targets markets where the number of power rails are large and therefore requires power management functions. However, volume is not large enough to justify the development of a full custom PMIC. AnDAPT gives freedom to the user from being limited to catalog discrete power devices at 0 NRE. AnDAPT's flexibility of hardware, along with the web browser-based GUI, provide users with key advantages in several areas. These include optimized power delivery, smaller system area, and rapid customization, amongst the many others in this power management ecosystem.
This slide gives a brief overview of AnDAPT's unique on-demand PMIC platform. The platform allows the user to develop a customized solution in a matter of hours or days, as opposed to a full silicon development, which can take from months to a year. This is achieved by having a variety of uncommitted resources that can be configured for each application. The resources here are covered to show the device's flexibility, while the user does not need to know the details of any of these resources, because he will receive all of his IP in a drag-and-drop environment. The IPs, as we call them, are power components, and these can be buck regulators, buck boosts, any of a variety of power topologies. They're available in a drag-and-drop web-based environment, which we'll cover in the next part of the presentation. Getting into details on these resources, the largest resource in the silicon is the power block. The power block includes an integrated MOSFET. The MOSFET is a 6 amp rated MOSFET, 20 volts, and there's 8 of them on the silicon. Included in the power block is all the driver resources, be it a linear driver or a high side driver or a low side driver. So it could operate for LDOs, high sides, load switches, low side, etc. Along with the MOSFET and the driver, also included in there is integrated current sense, which can be used for cycle-by-cycle current limit. It can also be paired with our DAC to do current mode control as well. Moving up, we also have 8 error digitizers, adaptive digitizers as we call them. These are optimized ADCs for control architectures and control algorithms. Along with the ADIs, we have 8 compensation memories. These compensation memories are optimized math PID engines associated with the memory that can implement digital PID loops, and they form the heart of our digital error amplifier. The compensation memories sit on a digital fabric. The digital fabric provides a parallel operation of the power box. The fabric also has 512 lookup tables, almost like a world's smallest FPGA, like in nature. Because the fabric is parallel in nature, we do not have to overclock an MCU core, for example. And often in my previous companies, we ran MCU-based digital power solutions where for a 1 megahertz regulator, you ran a 24 megahertz core, or even faster. In our topologies, the fastest clock we distribute throughout the chip is the switching frequency. So if you're building 600 kilohertz regulators, the fastest clock we're really distributing is a 600 kilohertz clock. This helps for power consumption as well as for EMI reasons. Also included on the silicon is 2 silicon oscillators in the timer array. These silicon oscillators are what generates that switching frequency. They can typically run anywhere from half a megahertz up to 32 megahertz. The faster clocks will be used for other applications outside of power typically. For power, you just run it as a switching frequency, like we said. Also included are there is local precision oscillators for DPWM resolution, or etc. We can have local oscillators that can run in nanosecond resolutions to achieve the high DPWM resolution. In addition to the clocks and the precision modulation timers that we talked about, we have 32 uncommitted comparators. They can be used for various applications for VNU, VLO, etc. Also, we have 24 programmable references. Those references can set up your regulation points and a variety of other things. We have 2 primary interfaces to the chip, an I2C interface for command and control, and an SPI interface that will give the part the personality. And whether there's going to be 2 non-sync bucks, 2 sync bucks, 2 LDOs, or what application you're going to use this for. So this goes over the resources on the chip and how the customer can utilize it. The next part of the presentation will go into the actual tool. We can dive right into our web tool here. The web tool is available from a Chrome browser anywhere you can connect to the internet. Once you've registered a website, you have access to the WebApp toolchain. The first thing the customer would do when you get in here is you create a project. I've already created one called Demo 1. The next thing you would do is you'd select a platform. Our B platform was recently released. With that, we can select the 8 MOSFET family, 6 amp current rating per MOSFET. We have 2 primary packages that we have, a 5x5 and an 8x8. We'll go ahead and pick the 5x5 package here. Going real quickly here, we've got the same diagram that we used, similar diagram to what we used earlier to explain the details. We have 2 fixed LDOs, a 1.2 and a 3.3 that the customers have access to. Additionally, we have 2 programmable LDOs. The customer can choose a preset voltage or pick a custom voltage that they'd like to set, and anything they want here. Once they set it, the regulator will then come up in that voltage. In addition to the LDOs on the base silicon, we have an OTP block that can be used to tell the system that the power has gone into a thermal shutdown, and it can be brought out on a GPIO signal. Additionally, we have our onboard clock that we've referred to earlier. The silicon has 2 oscillators here. Right now, we've set one to run at 4 megahertz and be divided into 7 equal phases at 571 kilohertz. You could just as easily bring a clock in from a pin or do a different divide ratio or different phasing of the clocks here. The second clock where you have on the silicon is running at 2 megahertz and running anywhere from 1 meg down to 8 kilohertz here. So that is the base silicon here that the customer would utilize here. In addition to that, on the left-hand side is a library of power components the customer has access to. And this is a constantly evolving library that can be updated to have more power components and different resources as well. In addition to regulators, we also have sequencers inbuilt, as well as digital logic capability and a variety of other things, that research generators that we can build, and a variety of other things that can be implemented on the same silicon. For this example, I'm going to drag in a buck regulator here. This is a synchronous buck regulator, so it uses 2 MOSFETs. If I want to duplicate, I can control, drag, and duplicate that power component. I can also drag and drop an LDO here, for example, which would use a single MOSFET. I can drag in a sequencer. A sequencer would only use the digital fabric. Similarly, I could also drag in a GRMOS for higher current applications. But it's literally this drag and drop ease to customize it. Once you have something that you like, then you can go ahead and select how you want the pinout to look like and where do you want things to connect to. So here I'm connecting the enable to the sequencer. I'm running the feedback to a GPIO signal. All 24 of the GPIOs are both analog and digital, and the tool is smart enough by context to figure out where it should be, how it should configure those. So I'm just doing this here. I'm not going to go through all of them. We can, at a later I'll just jump to a design that's pre-wired. But here, let's get into one of the buck regulators and get into the details of how to implement a buck regulator. As you would have noticed, when I dragged and dropped the buck, it also dropped in the external circuitry here. The first thing I'm going to select is the switching frequency here, 571 kilohertz here. I can select in the first 0 phase. Next thing is the input voltage. All the voltages here can be named so you can see it on the schematic, as well as when you track your design, it'll show up on the next cover sheet. You can also name your output voltage, set it here. The next few parameters are used to compute the LC tank circuit here. So if I select a 40% ripple here, it's going to update my inductor size here and say I don't need quite that large an inductor. I can use a 0.788 microhenry inductor here. 0.788, of course, is not a standard value. We've integrated a BOM tool to help you find a standard value inductor. Here's where Wurth's great REDEXPERT tool kicks in. And we've interfaced with them to develop this tool here. We can click Wurth here, and this will get into a live scrape of the website. And it's now going to give you a list of Wurth parts that are available here for the customer to choose for their application. So after a few seconds, the live scrape of the website will return all the Wurth part inductors that make sense for this application. The first column here is the data. You can pull a data sheet. We have the inductance value here, which we can sort by. Next is some of the key parameters, the DCR, the rated current, the saturation current, the size, which series it is. And thanks to Wurth, AC losses are also here predicted. It's difficult to get from a lot of inductor manufacturers, but with the strong partnership with Wurth and REDEXPERT, we can get this right from the tool. Additionally, you can order samples here, as well as get into the REDEXPERT tool directly here and look at some of these inductors. So if I go down here, I'm going to pick one of the 1 microhenry inductors here. And this is if you click this, this is going to launch REDEXPERT, and it's a perfect spot for me to let Quentin take over and pick up here.
All right, thank you, Ran. Thank you for the introduction of the WM tool. For my part, what I would like to do today is actually give you a more in-depth explanation about the REDEXPERT software, which is partially integrated into WebAmp, but has some more function which you can use directly into the REDEXPERT software itself. So this tool is cloud-based, so you can access it through any browser really. And the third thing that you will notice when you actually go to this link is that you may be asked to actually log in. You're not forced to do so. Most of the important functions are already accessible for login-free users. But if you want to log in, you're welcome to do so. And what it will do to you is simply give you a quick access to free samples, do some quotation requests for the tool, and a few other functions which you can demonstrate later on. So a little bit more about the tool itself now. As you can see, it has different modules here, and that's basically trying to understand what's your angle of approach of your problem. So maybe you are directly interested, you know exactly what components you want, so you're going to use this module and pick up a component that you're trying to pick. If you're not, maybe you want to have a specific approach based on EMI's filter design, and then you can use this tool. Or you can also look at it from a point of view of a power stage design, and then you can use this one. Now, today I would like to focus on a specific module that's called the power inductor module, simply because there is already a lot to say about this module, and also because I think it relates better with WebAmp software. Now, first thing that you can notice here is you kind of have 3 sections in this window. On the left here, you'll see all of the modules, simulation modules that you can pick from. In the middle, you have all the tables with all of the list of parts which you can scroll in with all of the properties and characteristics. And at the bottom, you have the curves, and you have actually, because it's the power inductor module, you have the saturation curves and temperature rise curves. So now let's go ahead and do a first test. I'm going to do a synchronous buck converter, and I'm going to use the example that Ran was mentioning earlier with a 12 volt in, 1 volt out, 6 amp, and the 571 kilohertz frequency. I'll let the 40% ripple current right now. So the first thing that I want you guys to notice is that REDEXPERT automatically creates the filters for you at the top of the table. And that's one thing that's annoying a lot of people I know, because a lot of people, when they go on REDEXPERT for the first time, they're not trying to select a part. They're trying to confirm what the experiment that they already have done in their lab. So they're trying to reproduce what they have done and confirm if the losses that they measure is the same as the one that we estimate, just to kind of confirm that the software is reliable. So no, the problem with those filters is that they're kind of generic, and they might actually lead to disqualify some parts that you think could actually work because you have maybe different work conditions. I don't know. So what I would encourage you to do is remove those filters if you already have a part number that you know you want to test. So you can enter your part number right there if you want to, but if this part number doesn't fit into those filters, it will still not show up. So definitely recommend delete the filters, just enter the part number. That's it for that part. So those filters, as I said, very generic. It'll give you, you can see single inductor, saturation above 7.2, rated current above 6.06, and kind of an inductance range here between 468 and 870 nanohenry. And of course, we want to be conservative and keep the pot temperature below 80 degree Kelvin. And you can feel free to add or remove any of those filters at any time. So for example, here I want to remove this temperature filter, and I also want to maybe narrow down my inductance value. Let's make it 500 nanohenry. Now you can, maybe, I don't know if you saw it, there was a twitch here and the list automatically updated itself to remove all of the values, all of the inductors, sorry, that do not fit those filters into those filters. So now the next thing that you can do is actually display some details here on the left. And what it tells you is give you some more details about the part in this particular application. So you can see the voltage across the part, the inductance, the current, sorry, going through the part, and you can see the peak values, minimum values, and you'll also see at the bottom the losses. Now, what's interesting about it is not only you see the total losses here, but you also see the split between the AC losses and DC losses. And the way we do this is simply by measuring the part and entering the value into the software. So that's kind of different than what our competition is doing. A lot of our competitors are simply simulating, calculating the losses based on maybe Steinmetz equation and maybe some kind of geometric approximation of the part. But what we found is that it's actually very, very hard to do this calculation accurately. And we found it much more accurate to actually take the part, measure it in different conditions, and kind of extrapolate those values to be able to provide an answer for every single case. That's what we're doing here with REDEXPERT. The third value that you can see is also the temperature difference here. So you can see, for example, in this case of this part, it's about 25.2 Kelvin rise in temperature. Now you can see that the part that the result we're seeing is for this part right there, the WEMAPI, and you can see that it's actually the one that's highlighted here. So if I switch line, it will switch as well here on the left, and it will switch the results here. Another thing is, as soon as we actually created the filters, some columns appeared here into the table, and you can see that you have a AC losses column, DC losses column, total losses column, and temperature rise column. So that's kind of the same thing we have here, except this is for all the parts. So one thing that you might want to do is simply, please show me, ask the software, please show me the lowest losses part for this design. And that's what you can do by simply sorting the values here, just like in an Excel file. Now, yeah, that's all good. I mean, okay, we're missing some values here clearly, but for the most of it, you can see that, oh, this part seems to have the lowest losses overall. But now you may think, okay, that's great, but I have some other conditions. And for instance, this part is just too big for me. 13 by 13 by 6.5 is way too big. So let's go ahead and create some more filters. Maybe I want to reduce the height to 5mm maximum. Maybe I want even to reduce it to 4mm to make it harder. There you go. So now I have a restricted list of parts that could fit this application. Now the next step to compare parts together, because we have a very small number here, is that we can simply use this checkbox here on the left. And you'll notice that this part have been put into this bar right there. And the great thing about it is that you can keep adding parts to this bar. So I can add multiple parts, and as you can see, the saturation and the temperature rise curves are actually overlapping, and you can compare the part behavior within each other and compare them with current. Another good thing about these graphs is actually you can change the temperature and see what's the behavior at different temperature. So for instance, here at 60 degree, the curves have slightly changed, and you can compare the part behavior at different temperature. Now, at this point, one of the things that people want to do is ask their colleague an opinion. Yes, we're working in the team environment, and quite often we want to know, hey, would you like to have a look at what I found? What do you think is the best choice? REDEXPERT has a built-in function for this, and that's simply the share button here at the top of the screen. So if you click this button, you'll have a link that you can simply copy and send to anybody. And the person that's opening the link into any browser really will have exactly the same thing in front of her or here than what you have. So you guys will have the exact same starting point. And I think that's great that you actually don't have to go back and do your simulation yourself, enter the parameters. So there's just much less room for error in this process. Now, another interesting insight about REDEXPERT is this temperature rise indication here at the bottom left corner. This temperature is actually a direct estimation from our temperature rating measurement, or current rating measurement, sorry. So what we did is, what we do actually when we measure the rated current of a part is put it on a single layer PCB, and which means the heat dissipation of the part at this point is less than optimal. It's actually very bad. So the part tend to heat up the most in these conditions. And I'm saying this because if you use a very small part on the 6-layer PCB, then your heat dissipation is going to be tremendously different. So the temperature reading that you'll see here in REDEXPERT will be maybe 10 times higher than what you'll have in real life. And that's unfortunately something we cannot really correct because we wouldn't know how to correct and how to guesstimate what are your typical application characteristics. It's very hard to estimate the heat dissipation losses for each different part for each different number of layers. So that's why we have kind of this number, which is, would highly encourage you to consider it as a worst case scenario number. Now, another thing that you can do is also add all of these parts into your cart, and you can either send an email directly. If you already have a Wurth contact, that's probably the easiest way to address him an email with a component that you're interested in. Another way is to simply ask directly for free samples through the REDEXPERT tool. What it does is simply opening a new tab for you, and what this tab is about is you can see that the part that you already selected are already there. The only thing that you have to do is indicate the quantity that you would like us to quote about and the amount of samples that you wish to receive. Also, we're asking you some information so that we can reach out to you later. It's a great way to, if you never engage with WurthElektronik, get in touch with someone at Wurth, and they'll be helping you with the REDEXPERT process, but also with the sample process. Now, another great thing about REDEXPERT is that everything is editable at all time. For example, if I wanted to change my rated current from 6 amp minimum to 9 amp minimum, I can just do so instantly. And you can clearly see that the list has changed. And the part that I previously selected some of the parts are actually grayed out. So for example, this map is grayed out, and you can see that the lines in the graphs also dashed. That's just to clearly indicate to you that this part no longer satisfies the conditions of the filters, and you're no longer able to see the losses estimation for this part. If you want to be able to see them again, well, either you can delete those filters or you can edit them back to 6 in this case. Now, I'd like to point out some limitation that you can encounter on REDEXPERT. The first one of them is the temperature rise in the inductor. Now, this value we give you right there is based on the rated current measurement that we do for our parts, for our rated current measurement. These rated current are actually done on single layer board, and the thermal dissipation on this board is minimum. It's actually the worst case scenario. So if you happen to select a very small part and you put it on a 6-layer board with forced air cooling, well, you might end up measuring a temperature that's ridiculously low compared to what we're giving in REDEXPERT. So I'll definitely highly encourage you to consider this number right there as a worst case scenario value. So that's for the temperature. Now another tip is about the buck synchronous converter module. A lot of people are often confused, like how can I simulate my continuous mode? What should I do to simulate this continuous mode? Well, the buck synchronous converter is perfect for continuous mode because if you change the duty cycle or ripple current, if you want to go to the extreme, well, this mode will actually let you have negative current and will even account for the inductor losses with those negative current. So that's a perfect mode for continuous operation. Now, if you want to do discontinuous operation, I would highly recommend you use the buck non-synchronous converter here module. It works exactly the same way, except you can see instead of having 2 MOSFETs, you actually have 1 MOSFET and 1 diode. And you're absolutely free to adjust the diode voltage and choose to have it at 0. That's perfectly fine, it will still work. But the diode will prevent any negative current, and therefore the losses estimation of the inductor will be based on 0 current when you're in the discontinuous mode. So instead of having the negative current estimation. So feel free to do that as well. By the way, you can clear the bar right there by simply doing clear out here if you don't want to have any of those displayed. Okay, and so last thing, everything that I've talked about of a buck converter is also available for the boost converter. We also have a CPIC module here. Now the particularity of a CPIC converter is that you can choose to use 2 separate inductor, or you can also choose to use a coupled inductor. And the source will let you toggle between those modes, and will eventually let you select all of the coupled inductor from all of the coupled inductor that we have at WurthElektronik. And if you don't want to go through any of those modules, you can simply choose to use the losses module, which will actually be much more straightforward and ask you directly what's your frequency, your duty cycle, RMS current, and ripple current. And just based on this, it's actually capable of giving you the losses for different inductor value, for different inductor. So that's it for my part on REDEXPERT. Before to pass it back to Ryan, I'd like to point out that REDEXPERT again is not only for power inductor, it's for a lot of our components. Almost all of our components are into this software, and whether it's MLCC, actually WebAmp is also using the MLCC module. It can also be LED, it can be RG45, it can be LAN transformers, it can be a ferrite common mode choke. I mean, you name it, and every module has tools specifically oriented to help you select this product. So feel free to reach out to us. We'll be happy to help, guide you through REDEXPERT, and in general, guide you with your design. I'll pass it back to you, Ran.
So now that you've learned all about REDEXPERT, we can go ahead and pick one of these inductors here. I'm just going to pick this one here. It's a 1 microhenry inductor here. Once you select OK, and it's going to pull that data back into the Webpack tool and update some of the parameters based on that. So here the ripple current will get updated, for example. Similarly, we can select induct capacitors as well using Wurth's tool here. So I'm going to go ahead and say we're going to use 4 pieces of the 47 mic 0805 package. So sort by the capacitance here. This is what we actually use in our boards here. Select that. And it's going to pull those values back into the tool. So based on these parameters, not only have I updated the ripple calculation, also I can use that to update a Bode plot. The Bode plot is the compensation for this regulator. This is the default Bode plot. If you don't like what you have there, you can click this little gear and tune it to however you'd like the behavior of the loop to respond to. So you can increase cutoffs, increase phase margin, move the zeros around and the gains around here. Once you have something you like, you can click back here and go back to tuning the rest of the parameters here. So in addition to the controller, we have all the standard protections that the customer's used to expecting. V and UVLO that can be programmed to output UVLO, cycle by cycle current limit, OVP, soft start slew rates are programmable, power good thresholds are also selectable. And also, with REDEXPERT's capabilities, we also have an efficiency plot here. And this is correlated in our bench and correlated with REDEXPERT's modeling, and we can present the AC losses here of the regulator. So that's the basic key parameters here of a buck regulator. We have similar features, of course, in the linears as well as the sequencer as well. Once you have a design here, I'm going to jump to one that I've wired up here. Once you have something here, you can move it around and you can do all the configuration stuff. I'm going to jump here to a pre-configured design here, which is going to take a second here. Let me just open up demo 2 here. Don't save this. Split second later, this is the regulator that we have here. In this, the other thing I didn't mention on the previous one, but you can as well, you can name different pins here. So we can rename this VFB linear, and that's the feedback signal for the linear. And it's that easy to change pin outs and change pin names, and they also show up on the diagram here. Before I go away from this screen, I want to show you a few features on this screen. In addition to the design view that we're used to looking at, we also have a pin out that's available for the customers, as well as a thermal view. And this will show you what the expected thermal dissipation of the package is. So for example, if we increase the current in one of these rails from 3 amps to 4 amps, we can see real time that the dissipation increases in the package here as well. This is based on our real world measurements that we've seen on our boards and seen for what thermal is. This kind of lets you know how much you can implement inside of a package. The next view is a graphic that you can save for this top level. Also, what we can generate right now is a custom data sheet. So what this is now going to generate is a custom data sheet for this application, not just a base data sheet for our part here. I'm going to go ahead and save it to the desktop here real quickly. Replacing a previous file generated. So now this is a data sheet for my demo 2 part. You could have named it whatever you want, and that would be the part. Here is features of that data sheet now as well. I'm going to fit it to the page here just real quickly here. So this is our standard part, and then your particular application here. So in here we're using 2 buck regulators, a linear regulator, as well as a sequencer. Here is the design view. Here's the package view that we talked about. Here's the pinout, a physical picture, as well as then each of the parameters for each of the regulators and the efficiency models there. And then a complete BOM of all the parts that you've selected, and so forth and so on. And this goes into all of the details of the regulators. Going back to the web tool, once you have this design, you can click compile here. Right now, once we click compile here, in the cloud, it's going to go compile this design real time. The primary files for customers of interest is the last 3 here in the right hand column, which is an Intel hex file format to pre-program a flash, an HAX file format that can directly program our part, and a bill of materials file that includes all those great parts you selected from REDEXPERT and integrated into a single CSV file. This will typically take a couple seconds to finish the compilation. Once the compilation is finished, on the left-hand side, this just gives you some resource allocation. It's a 30-second compile here. From here, we can go directly to the AmpLink tab. The AmpLink tab is our USB interface that we have that'll connect to your hardware and directly program the part. If you don't see something you don't like, you can go back and go through this process again, taking a few minutes, and change your output voltages, recompile, and download it to the part. It's literally that easy from this interface to do your development. Thanks for your time. Let me know if you have any questions.
AnDAPT provides many evaluation boards. One example is the AND 7220 PMIC. This board features Dr. Moss and Synchronous buck regulators, LDOs, and sequencing. Using our web adapter or WebAmp tools, our customers can customize their PMIC as many times as they want in their own office and within only a couple of minutes. All this without having to solder or change any of the components. Please see the link below or on our website for a full demonstration video on how to use the software-based customizable technology.